Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
When the latest transmission from the James Webb Space Telescope finished processing, the data appeared routine at first. Another scan of a distant galaxy, another supermassive black hole feeding at its core. Then someone noticed the timing, a burst of radiation, followed by something that shouldn't have been there. A secondary signal, delayed, warped, but unmistakably structured. For a moment, the room went quiet. Because if the models were right, if decades of black hole theory were correct, that signal had no business existing. Black holes are supposed to be one-way doors. Once something crosses the event horizon, it's gone forever. No light, no reflection, no return. And yet, just seconds after NASA scientists overlaid the raw Webb data with gravitational models, they realized something unsettling. The region near the event horizon wasn't behaving like a silent boundary. It was behaving like something was happening beyond it. To understand why that matters, we need to remember what black holes were always supposed to be. Black holes form when massive stars collapse under their own gravity. When nuclear fusion can no longer push outward against gravity, the core implodes. If the star is heavy enough, nothing stops the collapse. Not radiation, not atomic pressure, not even space-time itself. The result is an object so dense that escape velocity exceeds the speed of light. That boundary, the point of no return, is called the event horizon. The event horizon isn't a physical surface. It's a region in space-time where all possible paths lead inward. Cross it, and no signal can ever come back out. For decades, physicists treated this as absolute. Whatever happens beyond the event horizon is causally disconnected from the rest of the universe, invisible, unrecoverable, final. At the center, according to Einstein's equations, lies the singularity, a point of infinite density where curvature becomes infinite and our mathematics break down. Infinity in physics is a warning sign. It tells us the theory has reached its limits. But even with that unresolved core, the outer picture seemed stable until quantum mechanics complicated everything. Quantum theory insists that information cannot be destroyed, not erased, not permanently hidden. If you burn a book, its words are scrambled, but in principle, the information still exists in the arrangement of particles. Black holes appear to violate that rule. Throw a book into a black hole, and every detail about it seems lost forever. This conflict between general relativity and quantum mechanics is known as the black hole information paradox. For decades, it remained theoretical. Now we have instruments powerful enough to test its edges, and that's where James Webb enters the story. Unlike earlier observatories, Webb observes primarily in infrared wavelengths. That allows it to penetrate dense gas and dust in active galactic centers, the regions where supermassive black holes feed. When matter spirals inward, it forms an accretion disk, a rapidly rotating disk of superheated gas. Above it forms a corona, emitting intense X-rays and high-energy radiation. These environments are chaotic. Gas moves at relativistic speeds. Magnetic fields twist violently. Temperatures reach millions of degrees. Scientists expected turbulence, noise, random variability. But what Webb observed wasn't random. In multiple data sets, bursts of radiation were followed by delayed echoes, reflections that appeared to originate from regions geometrically hidden behind the black hole. At first glance, that sounds impossible, but Einstein predicted something extraordinary. Gravity bends light, mass warps space-time, and light follows that curvature. This phenomenon is called gravitational lensing. We've seen galaxies distorted into arcs and rings because of it. Near a black hole, the bending becomes extreme. Light can loop around it, orbit it, take curved paths that bring hidden regions into view. And that appears to be what happened. The delayed signals weren't breaking physics, they were obeying it in its most extreme form. Light from behind the black hole had been bent so severely that it reached us. That alone is remarkable. But the timing and structure of the echoes suggested something deeper. The radiation wasn't just bending, it was interacting. Some variability patterns matched theoretical predictions of reflections off the inner regions of the accretion disk, regions extremely close to the event horizon. We weren't seeing inside the black hole, but we were seeing how the edge behaves under extreme conditions, and the edge was not passive. The data suggested correlation, feedback, as if the boundary between inside and outside was more dynamic than previously assumed. This is where theory becomes critical. One leading attempt to resolve the information paradox is the holographic principle. It proposes that all the information inside a region of space can be encoded on its boundary. For a black hole, that boundary is the event horizon. Instead of information being destroyed, it may be stored, scrambled into subtle quantum states on the surface. If that's correct, the event horizon isn't just a dividing line, it's an active layer, a surface where gravity and quantum effects intertwine. Webb's observations don't prove this idea, but they are consistent with a boundary that behaves dynamically. And that forced scientists to pause, because if the boundary is active, then the classical image of a black hole as a silent vacuum cleaner is incomplete. There's another layer. In the 1970s, Stephen Hawking showed that black holes should emit faint radiation due to quantum effects near the event horizon. Hawking radiation implies that black holes slowly evaporate over immense timescales. Originally, this radiation appeared purely thermal, random, but if information is preserved, it cannot be perfectly random. It must contain subtle correlations, tiny deviations from noise. Webb cannot directly measure Hawking radiation from supermassive black holes. It's far too weak. But studying reflections and variability near the horizon offers indirect insight into how radiation behaves in these extreme gravitational environments. Each structured echo, each surviving correlation, each anomaly that refuses to disappear, it narrows the gap between theory and reality. Now consider the deeper implication. If information is preserved, if collapse does not end in infinite density, if the singularity predicted by classical relativity is avoided by quantum effects, then what happens inside? Some quantum gravity models suggest that instead of collapsing to infinity, matter reaches an extreme density where quantum pressure halts further collapse. The geometry may transition from contraction to expansion. From the outside, we see a black hole forming. From the inside, the physics may resemble the early universe: high density, extreme curvature, rapid expansion. This similarity is mathematical, not mystical. The equations describing black hole interiors closely resemble those describing the Big Bang. No, this does not mean NASA discovered another universe. It does not mean Webb literally looked inside a black hole, but it does mean our understanding of the boundary is evolving. Black holes were once treated as endpoints. Now they are laboratories, places where gravity and quantum mechanics collide. Webb's data didn't break Einstein's theory, it confirmed it, again, through extreme gravitational lensing and relativistic timing. But confirmation at the edge often reveals new questions, because when a theory survives extreme tests, we push it further and further until something gives. Just seconds after scientists realized what those echoes implied, the conversation shifted, not toward sensational headlines, but toward refinement. Models adjusted, simulations rerun, assumptions questioned. Because black holes may not be silent, they may not be empty, and they may not be final. They may be interfaces, boundaries where information is transformed rather than destroyed. And that quiet realization, buried in data and equations, may be far more revolutionary than any dramatic announcement. Something is happening at the edge of black holes, not something that violates physics, but something that forces us to rethink it. And James Webb has given us the clearest glimpse yet of that edge. Not what's inside, but how the inside may be connected to the outside. And that changes everything.